Let's have a quick review about what we have learned. What is the control problem that we have been dealing with? The control problem includes 3 elements. A dynamic model, which describes how the system works. Normally it's described by using a differential equation. And the performance index. And we started with the performance index in this form with only integration from T0 to Tf. And later on we expanded that to a performance index with a combination of a terminal cost S plus the integration form from T0 to Tf(v). The boundary conditions, we started from the fixed boundary condition. Xt0 is equal to x0 and xtf is equal to xf. So that is something we started with. And later on we expanded to a broader range of problems, allow tf and xtf being free. And we also got some conclusions which are summarized in these few equations. For us to get optimal control, we have a state equation need to be satisfied. The state equation is a partial L over partial x minus d dt partial L partial x dot is equal to 0. And the co-state equation is a partial L partial lambda, so we replace the x by lambda. And we also know that this co-state equation is the same as the dynamic equation. And optimal control, partial L over partial u minus d dt partial L over partial u dot is equal to 0. This is the same as partial L over partial u is equal to 0. So this term is 0. But if we put this in this form, it can be easily memorized. So we know that we just need to know one Euler Lagrangian equation. We apply that to the state x, to the co-state lambda, and to the control u. This will allow us to solve for the optimal control and optimal state. And the boundary condition is given here. Remember here, theta x is the variation of x at a time tf. And we haven't converted that to the variation of xf yet. So xf means the variation of the final value. And the variation of that final value is equal to the variation of that at a time tf plus the time derivative of x. This is the optimal control at a time tf. So this describes the slope of change times the delta tf. So we're going to replace this term delta x at a time tf by delta xf minus x dot times delta tf. Oh, sorry, this is the delta xf. We have 2 terms here. So one term is the delta xf, and the other term is the delta tf. We will have a partial L over partial x dot transpose times delta xf, which is this term. And the second term is minus partial L partial x dot times x dot at tf, delta tf. And combined with this term times delta tf, we have L minus partial L partial x dot transpose times x dot star evaluated at a time tf times delta tf. With this replacement, we get the boundary condition in these 2 terms. One is related to delta xf, and the other one is related to delta tf. Start from here, we're going to transition to Hamiltonian formalism. So before that, we want to know how we define the Lagrangian function. This is defined as v plus, we said ds dt plus lambda transpose times g, right? G is equal to f minus x dot. And what is the ds over dt? ds over dt can be written in 2 terms. Partial s over partial x times x dot plus partial s over partial t. So we can plug this back in there. This will give us the full expression of this Lagrangian. And for Hamiltonian formalism, we're going to define Hamiltonian instead of this Lagrangian. But Hamiltonian has a relationship with this Lagrangian. Here, if we define the Hamiltonian as v plus lambda transpose times f, we define this differently from that. And let's see, if we define the Hamiltonian like this, what happens to those equations? The state equation will become something else in terms of the Hamiltonian. Let's see what that is. L can be written in terms of the Hamiltonian. So this L will be equal to V that is captured by this Hamiltonian and lambda transpose times F that is captured. So over here G will left with a minus lambda transpose times x dot, and the rest is combined with the V that become the Hamiltonian edge. And we can plug this back in there. That is the partial s over partial x times x dot plus that. So this will give us the relationship between the Lagrangian and the Hamiltonian. So partial L over partial x, that will give us a partial h over partial x, and the rest are not a function of x. Partial L over partial x become partial h over partial x. And how about a partial L over partial x dot? Partial L over partial x dot, this one gives us a negative lambda transpose. By replacing this L in terms of this Hamiltonian function, we'll get a partial h partial x that is equal to negative lambda dot. The solution to that equation gives us the relationship between optimal state and optimal co-state lambda. And if you apply this to the control U, to the optimal control, and we know initially the optimal control we have is a partial L over partial U that is equal to 0, right? And let's look at what we have here right now. These are not a function of U's, so we know that a partial H over partial U that is equal to 0. So this will allow us to solve optimal control. And the co-state equation, so initially the co-state equation is also the constraint, which is also the dynamics. So the co-state equation, and if we define the Hamiltonian like this, it will give us partial L over partial lambda. This will become partial H over partial lambda, and over here partial L over partial lambda dot, that will give us x dot. So putting that together, it becomes partial L over partial lambda is equal to x dot. And what is this? This is also the dynamics, right? So let's look at the boundary conditions. So initially the boundary conditions is given in this form, and we're going to replace L by using the Hamiltonian. So that will give us the new boundary condition in terms of the Hamiltonian. L will be replaced by, this will be H plus partial S plus T evaluated at TF times delta TF plus partial S partial X at the optimal. So we use a star to represent that, right? Minus lambda star transpose evaluated at time TF times delta XF is equal to 0. Or these are Hamiltonian formalism. Let's have a quick recap about how we use this to solve the problem. The procedure to solve the problem, by introducing Hamiltonian as this function, V plus lambda transpose times F. And remember, F is everything on the right-hand side of the dynamic equation without the x dot terms. And we'll have a new result. And this new result looks more compact compared to the Lagrangian formalism. And we have the optimal control is in the same form, partial H partial U is equal to 0. This can help us to find optimal control. And this optimal control over here is not a function of a time t. You're going to find the relationship between the optimal control and the co-state. And on top of that, you have some other relationships. The state equation becomes partial H partial X is equal to negative lambda, which is much easier compared to before. We need to do the partial L over partial X dot, right? Right now, you do not need to do that anymore. And a partial H over partial lambda, which is a co-state equation, and this is equal to X dot star. And this is the same as the dynamics. And toward the end is the boundary condition. The way to use the boundary condition is the same as how we used this before. So it depends on whether TF is free or not, and delta XF is free or not. It's totally fine that if you only have one state that is free and the other state is fixed. So in that case, you get different equations. That is something you need to pay attention. So I summarized the procedure how we solve optimal control problem by using Hamiltonian. The first step is form the Hamiltonian. The Hamiltonian is equal to V plus lambda transpose times F. The second step is to find optimal control. Partial H or partial U is equal to 0. It's very likely that you're going to find a relationship between the optimal control and the states and the co-state. Eventually, you want to find the optimal control at the time t, right? Next step, we're going to plug this control into the Hamiltonian. We find the optimal Hamiltonian. After we find the optimal Hamiltonian, we're going to apply the results that we got just now. Partial h over partial lambda is equal to x dot, which is the same as the dynamics. This is our dynamics equation. And the next one is the co-state equation. The co-state equation tells us lambda dot is equal to negative partial h partial x. The boundary conditions are given in this form. Depends on different conditions that you are giving, you will have a different boundary conditions. And if a TF is fixed and XF is also fixed, it means this is 0 and this is 0. This condition always holds. In that case, you don't need to deal with this anymore. And in case delta F is free, it means this coefficient has to be equal to 0. If XF is free, the coefficient to delta XF has to be equal to 0. So that's how you get different boundary conditions. The boundary conditions are summarized in this table over here. In total, you have 5 different cases. So let's look at one example. We have a second order system giving as x1 dot is equal to x2, x dot is equal to u. The performance index is this. We do not have a terminal cost. x0, the initial condition, is equal to 1, 2. And the final time, which is 2 seconds, it's fixed, which is also very nice. You know that when it's fixed, delta TF is equal to 0. And the final state, XF, is 1, 0. It's also fixed, which is also nice. Delta XF is equal to 0. So this is the first case, right? And the step 1 is form the Pontryagain Hamiltonian function. So it's V plus lambda transpose times F. It's no longer the constant G. We do not need to write the dynamics in that form. F have 2 terms, right? The first row is x2t, and the second row is ut. x2t and ut. They are a function of t. I'm not carrying that over for all the places, otherwise it will be too hard to write. But when you write it on the report, you need to write that out. The Hamiltonian is a function of a state, co-state, and a time t. And the function v is equal to everything inside the integration, right? How do we find the optimal control? The optimal control are obtained from partial h partial u is equal to 0. Second step, partial h partial u is equal to 0. Let's see what we have here. So h is equal to, the v function is a half u squared plus lambda transpose times f. So lambda transpose, lambda has 2 terms, the vector with lambda 1 and lambda 2, because you have 2 states. So plus lambda 1 times x2 plus lambda 2 times u. Now we can find the optimal control. Partial h over partial u, that gives us u plus lambda 2 is equal to 0. So we find the optimal control u is equal to negative lambda 2. So we find the optimal control. So after we find the optimal control, we're going to submit this u to the Hamiltonian, so we'll be able to find the optimal Hamiltonian. So step 3, we're going to find the optimal Hamiltonian. And then we're going to replace u star by lambda 2, right? So now we have a lambda 2 here. And u, this will be replaced by negative lambda 2. So we have a negative lambda 2 square. So we already got a positive lambda 2 square there. You got a negative lambda 2 square. So that will give us negative half lambda 2 square. So we find the optimal Pontryagain. So step 4, we're going to apply the state and co-state equation, right? Step 4, solve the set of differential equations. The co-state, this will give us the dynamics equation. X dot is equal to partial h partial lambda. Let's see what that is. X dot at optimum, that is equal to partial h over partial lambda. And these are evaluated at the optimal states as well. This will give us 2 equations. The first equation is x1 dot is equal to partial h partial lambda 1, partial h partial lambda 1, that will give us x2. And x2 dot, this will be equal to partial h partial lambda 2. partial h, partial lambda 2. That will give us negative lambda 2. These are all in the optimal states. You might be wondering, what is this? This is not a u. Look, negative lambda 2 is equal to u. So this is why we said this is also the dynamics equation. Okay, we got the differential equation applied to this co-state lambda. Next equation is lambda dot. The co-state equation lambda dot is equal to negative partial h partial x star is equal to negative partial h over partial x. The same thing, we have two equations, right? One is about lambda 1, the other one is lambda 2. So lambda 1 dot is equal to partial h over partial x1. Partial h over partial x1. And in the optimal Hamiltonian, we do not have x1. So this will tell us lambda 1 dot is equal to 0. And how about the second equation? Partial h over partial x2, that gives us lambda 1 with a negative sign, which will become negative lambda 1. Alright, let's see how many differential equations we have. 1, 2, 3, 4. We have 4 differential equations. And there are 4 functions we are trying to find out. So let's solve these differential equations. From this equation, let's solve these differential equations. We find that lambda 1 is equal to a constant. Let's use a C1 to represent a constant. Now we can find a lambda 2. Lambda 2 star is equal to, you do the integration of this, that will give us a negative C1. Remember, there is a negative sign in there. A negative C1 t plus C2. After we find a lambda 2, we'll be able to find x2. x2 dot is equal to that, and we'll do the integration. That will give us x2 star. So that is half C1 t squared minus C2t. Be careful, there's a negative sign there. After this, we can find x1 star. So x1 dot is equal to x2. We need to do another integration of this. So that will give us 1 over 6 C1 t cubic minus half C2 t squared plus C3. We missed a constant here. So we'll carry that over. We have C3 times t plus C4. Next step is to apply the boundary conditions. Apply the boundary conditions that will allow us to solve C1, C2, C3, C4. Step 4, apply boundary conditions. So we have 4 boundary conditions, which are given like this. x1 at a time 0. From this formula, we know it's a C4. That is equal to 1. And x2 at a time 0, which is equal to C3. That is equal to 2. And x1 at a time tf, here tf is equal to 2 seconds. We'll plug 2 into the formula. So x1 is this, so this will be 8 over 6. This will be 2c2 plus 2c3 plus c4, and this is equal to 1. And the last one is x2 at a time 2 seconds is equal to, plug everything into this expression. And this is 2c1 minus 2c2 plus c3. This is equal to 0. So now we have 4 equations with these 4 constants need to solve. We can solve them, right? So we already have a c4 and a c3. So c1 is equal to 3. c2 should be 4. And a c3, we already have that. c3 is equal to 2. And a c4 is equal to 1. We already have these 2. Now we found everything. We will know our optimal control and optimal state, right? And we already know u is equal to negative lambda 2. C1 t minus C2. And C1 is 3t minus 4. And x2 star, this is optimal state, that is equal to 0.5 C1. So that gives us 1.5 t squared minus C2 4t plus 3, which is 2. And the last one is 1 over 6 times C1, the 3, this is 0.5 t cubic minus 2t squared plus 2t plus 1. So this is how we find an optimal control and an optimal state.